Okay. And then in this rectangle, you have this, and eventually it will just be one rectangle in which you will have this. Does that work? Yes, that is also a way to do this. Okay. But I think today's talk, I'm going to keep it to this triangles, because you will see why. Yeah.
Awesome. I have a question, but regarding this, but I'll ask this based on how many slides you have left.
Okay. I have, I guess, okay, I have 30 more slides left.
Okay, I'll ask it at the end then. I'll come back to you.
Okay. 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 Yeah. So now, just to visualize what this kind of looks like, uh, so here is like a density distribution, high density in the center, very low density in the outside. And this is how the grid is. Okay. You will ask me, this is a triangle. This is not a triangle. This is like a polygon, bunch of polygons. They are not the same. Yes, they're not the same, but they're the same. I will explain you how these two are related, and that is where the beautiful old mathematics comes in. Okay. But as you can see, in the center, the cells are so small that it's just like blue dots, right? But at the edges, it's like so big. So this is how, uh, this kind of unstructured mesh is going to help resolve the regions where we are interested in. So if this entire thing were to expand, like I was showing, you start with this and you become this entire thing is going to move like this. Okay. uh, okay. Now, I hope it is clear why this technique is that important. The AMR technique, I hope I have conveyed you that this is like a crucial, central, like impossible to do anything else without this. Okay, it is that important to astrophysics today, and especially the simulations that we do. Okay, so now let me get to magnetohydrodynamics. Okay, why is that important? So you might have already seen this image, which is we start with a big bang, then there is the CMB, and then there are no stars, so the universe is very dark. And then here, basically after recombination, we have mostly neutral hydrogen, that is hydrogen in its atomic state. Okay. And then the first stars pop up, then the galaxies pop up, and now these stars are emitting a lot of UV light. Okay. What happens if your UV photon has energy greater than 13.6 electron volts? Hydrogen is now dissociated. The electron will leave the proton, and you have ionized hydrogen. So you form these pockets of ionized bubbles which contain ionized hydrogen. And soon these bubbles are going to expand in this phase called reionization, and then the universe becomes completely ionized. Okay. You have some pockets of uh, molecular hydrogen which are in the galaxies where the density is very high, so the light is not strong enough to ionize all of it. So that is where you have interesting things happening, but most of the universe is going to be fully ionized. Okay. So the estimates currently say that over 99.9% of all matter, like regular matter, is in an ionized state, so it's a plasma. And on top of this entire universe is populated with a lot of magnetic fields. Okay. So where are these magnetic fields coming from is debatable. There are two schools of thought. One who say like, okay, stars and galaxies, these form these magnetic fields and spread them in the universe. And then there is the other school of thought which says, oh no, these magnetic fields have always existed. They existed, almost as early as the CMB or even before. Okay. We don't know which one is true. People are working on it. But currently the universe as it stands has a lot of magnetic fields. Okay. In the galaxies and in between galaxies, it is quite weak. It's in the order of a few microgauss. But if you go to like very strong AGNs and blazars and neutron stars and stuff like this, magnetars, you will see magnetic field strengths of the order 10 power 15, which is like many many orders of magnitude larger, right? So now we know that the universe is magnetized. How do we describe this? How do we tell Like, how do we predict how this fluid is going to evolve? So that is the whole point. And we have to always keep in mind the divergence of magnetic field is zero. Always. Okay. So magnetic monopoles don't exist. They must always form closed loops. And we have to ensure they form closed loops even in our simulations. Okay. So um, this is a bunch of stuff, but basically these are the magnetohydrodynamic equations. Basically, there are four equations. They're all written as in this form, which is the rate of change of some conserved quantity is the change as the increase or decrease of some flux. Okay. So there is a conserved quantity which changes as the flux changes, and together the quantity is conserved. So it should all add up to zero. So when we talk about like magnetohydrodynamics, what do we have? We have the density of the gas. Basically, mass must be conserved. Don't have to write the notes. I'm going to send the slides. Okay. So the mass must be conserved, right? So that is the first equation. That is the density. The momentum must be conserved of particles. That is the second one. Energy must be conserved. That is the third one. And the magnetic field strength, because they form closed loops, and you don't have monopoles that are generating new fields. All you can do is, like, these loops exist. You can twist them, turn them, fold them, do whatever you want to do. But basically, it's a closed string. Okay, it's a closed loop. So that also must be conserved, right? So these are the conserved quantities, and this is how they are related to the fluxes. So these are basically how they change. Okay. Okay. So for reference, this T means this. Okay. We can skip that. But the next thing to keep in mind is we are talking about a gas. So it has some constraints. The gas cannot do whatever the heck it wants, right? So it must follow the ideal gas law. Okay. Which is in some form this is quite simple, because you know the pressure, you know the velocity, you know the density. So if you know two of them, you know the third one. So you don't solve for all three, you only solve for two, and the third object you fix using these two. Okay. So in these equations, we are evolving the density and momentum. So momentum has the velocity in it, right? So you basically have these two sides. So you basically fix your thermodynamics, which is the pressure and temperature, all of that from the density and velocity using this ideal gas law. Okay. So that is quite easy to take care of. But then there is the elephant in the room, which is divergence of a magnetic field is zero. Okay. This is perhaps the most difficult constraint to satisfy from all of physics that I know. Why is that the case? This magnetic field is a vector field, right? So at each point, to calculate the divergence at that point, you have to basically integrate over all the regions of space throughout your simulation box. Okay. Because locally it could be zero. You integrate over a fixed region around this point, it could be zero. But what if there are monopoles outside that region? That will then affect the things that are happening at this point. Okay. So, and this must be true at every single point. It's not like it is zero at the center or anything. No. So at each point in the volume, I must calculate what the divergence is by integrating over the entire box with respect to that point being the center, and then make sure it is zero. So this is fundamentally, computationally, very, very challenging, because if you want to evolve the density or temperature, or you want to find the pressure, you have the density at that point, you have the velocity at that point, and you have the neighboring points that will influence that, right? Let me make this clear with a drawing. Okay. So you have a box and it has some density. It has some density rho. And there is some flux or a mass, that is like some other fluid is entering this box through this phase. So the density will increase by some amount. This is quite easy to compute, right? Because all you need is what is the density inside the box, what is the amount of flux coming into the box. If you have, so basically this flux is going to come from the next box perhaps, right? So all you need is these two, and you have to basically do that on all these sides, right? So if you have, oh, we have some flux coming from here, some flux going out here, some flux going out here. Now, given these four fluxes and the internal density that I start with, I can just add them all together and easily get what will be the density at some t plus 1. Okay, this is density at t. Okay, and this is density at t plus 1. So this is like a local problem. But the magnetic field is not like this. Because it's a vector field, I need to integrate over all space. So that complicates our job quite a lot. Okay. So the next part of the discussion is going to be around how do we ensure this is true? Okay. How do we be smart about the way we solve for the magnetic field so that this condition is always satisfied, and let us also not explode our computational cost. Let's not make this more complicated than it absolutely has to be. Okay. So, like I was talking about here, right? The entire problem is we have some fluid variable in the cell here, and we have some other fluid variables in the cells surrounding it. Okay. And we want to solve for what happens after some time t or delta t. So this setup is called a Riemann problem. Okay. So basically concentrate on only this much. Okay. The rest of it is basically the same thing rotated around. So you have some fluid variables on the right side and you have some fluid variables on the left side. So these lines represent the magnetic field. Okay. So this is the one on the left. This is the one on the right. Okay. V is the velocity. This is the, on the left, it's moving to the right, and on the right, it's like on a diagonal side. And then there is the density and the pressure. Okay. So these are at time t equals 0, let's say. So now the Riemann problem is basically what is happening at this boundary. Okay. What is the change occurring at this boundary? So if you think about it, in a computational box, like in your simulation box, if you take any two cells, no, like they are not going to have exactly the same density. Okay, if they do, nothing happens across this boundary. Nothing happens. They're already at equilibrium. They have exactly the same properties. Nothing is going to change. Okay. If that is not the case, if there is any variation, basically because you're using these numbers to represent the left and these numbers to represent the right, it is basically like a step function with densities, some high density on the left, low density on the right, and there is a sharp change across this boundary. Okay. So classically, a Riemann problem always has a single discontinuity at this boundary. So there is a sharp change. Okay. Now, what does physics say? Sharp changes bad. We should smoothen them out over time. We can, depending on how much time we have, which is delta t, we can determine how much it will change, how much smooth it will get. And depending on the smoothness, we can update what the density is on the left, what the density is on the right. Okay. And then use those as the input for the next step and then propagate it forward. Okay. Okay. So now let's say we take the magnetic fields and solve them at this boundary. Okay. We ensure the amount of magnetic field that is coming into this boundary is the same as the magnetic field that is leaving this boundary. If we were to do that, it is not sufficient because what happens across this boundary is dependent on all other sides. Let's say there is magnetic field coming in from here, coming in from here, in from here, in from here. It is coming in from all sides. That will obviously violate your divergence B equals 0 condition. Okay, because they're all falling in. Or the other way around, if they're all going out. So if you solve just one boundary at a time, you will not get the right solution. Okay. So now, what are the problems? What will happen if we don't take care of it? Okay. Let us say we only solve it at one boundary at a time, and we end up with cells that have magnetic fields that are diverging. Let's say magnetic field goes out from here, out from here, out from here, out from here, all the boundaries, it's going out. So basically we have a monopole of magnetic field in this cell. Okay, so first thing that ends up happening is what, I don't know if you guys have studied this in differential equations in your first year, but so there are differential equations called hyperbolic, when you can describe the solution as a wave. So density can be described like the solution to mass conservation is basically a wave. It's basically like a sound wave. Okay, any change in density is going to propagate as a sound wave because the density change is going to move back or forth. Okay, just like that, MHD equations also describe some sort of waves which include sound waves. So there are sound waves, there are waves in magnetic fields, there are waves in energy, and so on. Okay, so they will no longer be described by waves. That is your first problem. Okay, so now they become very complicated. And then momentum and energy are no longer conserved. Okay, that is straight up violating basic physics you already know, so we should not do that. And then this divergence usually has a disgusting property, which is if there is a small divergence, it will exponentially start growing. Okay, so we start with, let's say in this cell, a very small divergence. Okay, if the field comes in only a little bit from all directions, within 10 steps you will see that it starts completely exploding, and suddenly you have a exploding like you basically start getting a divergence that is growing to infinity. That means your simulation is not going to run for much longer, it is going to stop there. Okay, and also they give rise to extra forces. Okay, just like, okay, think of instead of magnetic monopoles, think of an electric monopole, which is just a charge, right? You have a positive charge, let's say. What does a positive charge do? It starts exerting a force on all other objects that are in its vicinity, which are also positively charged or negatively charged, right? Just like that, if you put a magnetic monopole, it will also start exerting these forces. But these are not electromagnetic forces because you're not describing electromagnetism anymore. So all of these are coming up because you did not solve this boundary value problem properly, or okay, because you did not solve all the boundaries carefully. So computationally, how do you deal with this? People came up with something called the divergence cleaning method, which is let a divergence exist. After I solve my Riemann problem, I will calculate the divergence everywhere and subtract it. I will manually cut the divergence. I will calculate it and cut it to 0 on each and every cell. As you can think that this is complicated, as I already mentioned, this is also computationally expensive to do. But this will, instead of exploding this divergence, it will keep it limited within a certain extent, and it works quite well. Okay, now people have fairly better ways of doing this, more efficient ways of doing it, and this is still used in many MHD simulations. Okay, but the whole argument relies on the fact that you can artificially decrease or remove the divergence manually. Okay, can you do that or not depends on the problem. Some problems you can do it, okay, and some problems you cannot. Now there is a much better way of doing it, which is called the vector potential method. You already do you know vector potentials? Have you come across vector potentials in EM? Yes, no. If yes, raise your hands. If no, I don't know. Oh, they haven't? Okay, okay. Fine, I'll tell you. Have you guys done some like vector algebra at all, like vector calculus? Like, do you know curl, divergence? Do you know them? Yes, no. Okay. So, okay, we are going to rely on um, this simple rule, which is, oopsie, some vector field here. What is this? Exactly. Okay. So the divergence of a curl is always 0. Okay, we are going to rely on this. You can see what is the relationship here. We have the magnetic field divergence equals 0. Okay. Instead of solving the magnetic field, let us define the magnetic field to be the curl of something else, which we call A is what is called the vector potential. Okay. So we will define B equals del cross A. Okay. And we will solve A across the boundaries. Okay. And by construction, B will all like divergence of B will be 0. Okay. It's a simple math trick. You can do this. Okay. But here the issue is, as you can clearly see, after you define A, the vector field A must be differentiable. Okay, you are taking the curl of A to define B next. So A on itself must be differentiable. That is where astrophysics has a problem with this method, because in astrophysics we have something called shocks all over the place. Okay, you have supernovae, which are basically exploding stars, and as the star explodes, it sends a shock wave. And a shock wave, by definition, has a strong discontinuity behind the shock wave and ahead of the shock wave. Okay, so there is a sudden change in temperature, there is a sudden change in density, and as it happens, there is also a sudden change in the magnetic field. So if you were to like run a shock through your simulation box, your A will have a sudden change. It will basically have a sudden change like this across the shock front, and you will no longer be able to differentiate A here at the boundary. That means you don't have B defined at the shock, which is a problem, because that is not what physically happens. So this, as you can imagine, will give rise to issues, and I will show you what these issues are. Maybe we can go there. Oh wait, maybe we'll get there. Okay, so the shocks have this problem, and then the next one is called constraint transport. Constraint transport is basically, instead of solving at one phase at a time, you solve it across all phases simultaneously. Okay, you have basically multiple Riemann problems, and let's say if you have a square box, then you have 6 faces, and across these 6 faces you will solve them at the same time, and you will ensure that div B condition is always 0. Okay, a simple way of doing it is, so you have basically a box, and instead of solving for the magnetic field itself, you calculate the magnetic flux at the surface of the box. Magnetic flux is integral of magnetic field over some area, right? So you have a closed integral of B over some ds, some surface. Okay, so this is what you do. So your surface is the box face. Let's say this is your box. You basically integrate magnetic field over this surface, you get the flux at that surface. Okay, and the sum of all the fluxes should be 0. Okay, and if the sum of the fluxes is 0, then your divergence of magnetic field is 0. Okay, that is the whole idea. And because phi is an integration, if B has a sudden change like this, you can still integrate over this, right? Your integrals don't have a problem. So this works much better. So, and then basically you're using the Gauss theorem to do this. Basically, the sum of the fluxes through a phase is 0. And this is what it will look like. So you have your grid. Instead of solving things at the face, you're going to project everything onto the surface, which is here by this line. Okay, and you're going to solve for flux conservation on these faces. Okay, so yeah, so you basically have your magnetic fields in XYZ for a cell, and you do the integration. And because your size of the box is fixed by your resolution, you basically have something called a numerical integration, which is instead of dy dz, which are infinitely small, you have finite size of dy dz. Okay, and you basically have these fluxes, and your sum of all the fluxes through all phases must be 0. So you have 6 phases, and then you add them all, these should be 0. And once you solve this algebraic equation, it's a simple algebraic equation, you can then recalculate the magnetic field using this formula, right? Let me let me also mention this, like, okay, in your Riemann problem, basically you're looking at the change of magnetic field, right? If we go back to our flux conservation equation, we had something like this. So we had some conserved quantity, dB by dt equals sum minus del dot sum f, right? This is what we had in the equation, or it was written as this plus this equals 0, same thing. Now, what you have basically done is, instead of b, you're looking at integral of b now. Okay, you basically do an integration here, and this is what you end up with. Okay, so here this was the flux. After an integration, it is called the electromagnetic electromotive force, F, which is basically the integral of whatever the flux we had. Okay, so this is, we know the magnetic field from the previous step, we know the velocity from the previous step, so we can calculate what the F is. And once we know what the F is, we can calculate what is the change in the flux. Okay, so once we have the change in the flux, we can basically, we have already updated our fluxes to the new value of the flux. Okay, and then we can get the updated value of B for the next time step, and then we repeat that loop. Is that clear? So, I mean, it's going to look a little messy like this, but the nice thing is, this is what is used in almost all the modern MHD codes. I have given some examples here: Flash, Ramses, Athena, Enzo. These are codes that have been there for like 15-20 years now, and they all use this formulation. Okay, so let me show you what the difference is in terms of like application of this. So on the left is constraint transport, on the right is the vector potential method, and what we are trying to do is, we basically have a step function. Okay, a step function is called, it's a square wave, it's called a square wave, and this step function is moving. Let's say it's moving to the left or right or whatever. So so analytically it's a step function. So this is the solution, the dotted line, analytically. And when you use constraint transport, you get this. Okay, and as you can see, there is like a smoothing happening at the boundary. That amount of smoothing depends on your resolution. So if you increase the resolution, it becomes sharper. So as you keep on increasing the resolution, it approaches your solution. Okay, so this smoothing happens because of numerical errors. Of course, your computer has some round off error, as you know. Because of that, the solution is going to get smoother. But if you look at the vector potential, like I mentioned, whenever there is a sharp change in quantities, it goes crazy and it starts producing these extra spikes. Okay, these are not physical, they don't exist in our analytical solution, so these are problematic. Okay, this is the magnetic field. We can also look at the electric field or electric current. So basically, electric current in this case will look like basically two delta functions, which our constraint transport is approximating as a Gaussian, roughly. But the vector potential method, although this guarantees div B is 0, it is not calculating the same B field. It is calculating a different B field, which is given by this other function. Okay. So divergence B is still 0. One solution is accurate, one is not. Okay. So I think I hope I have convinced, like, okay, let me also show you some other, like, how does this compare to divergence cleaning method? Okay. But these are some more realistic examples. So here there is a galaxy using constraint transport on the left and using divergence cleaning on the right. Okay, it's called Powell's scheme. So what we are looking at is the gas density. So how is the gas distributed in the galaxy? If the magnetic field is correctly calculated versus magnetic field calculated with problems. Okay, as you can clearly see, the galaxy looks different. The density distribution is different. Okay, and the galaxies we see are mostly like this. They are like spirals, full spirals, with very dense centers. But over here, the center is less dense than the spiral arm, which is not what we see in our galaxies. So um, then let's also look at the magnetic field. So as you can see here, the magnetic field is in a very spiral pattern. But if you look at the right, the magnetic field is very high because of monopoles, and it is everywhere. It does not have any structure. It's basically like a mush. Okay. And when I was in Niger, I was working with Dr. Tuhin Ghosh and Luke Shamendi, where we were looking at galaxies and their magnetic field. And what we see is this: we see a spiral pattern, which is either exactly on top of the spiral arms of the galaxy. So it does look like this on the left, not like this on the right. Okay. Um, then this is the X component of the magnetic field. Okay. One more thing to look at is, okay, the whole point of doing this exercise was to look at how things evolve with time, right? That is what simulations offer us. And here is a time evolution. So this is the magnetic energy, the blue line. The green line is the energy in turbulence, which is basically random motions of the gas. Okay. And the orange line is the thermal energy of the gas. So of course, in the galaxies, gases are very hot, they're ionized, as I said. So thermal energy is very strong. Okay. Turbulence is basically because of mixing of gas. Like you have gas that is basically stirred or shaken, right? It is high at the start, but as you can see, over time, the magnetic energy increases, turbulent energy decreases, and they basically become equal to each other. This is a very strong observation we have from our local galaxies, where we see the amount of energy in turbulence is equal to the amount of energy in magnetic fields, which is also equal to the amount of energy in cosmic rays. Three completely different things. One is particles, one is gas, and one is magnetic fields. They all have they share the same energy density. That means there is some interaction happening that maintains that balance, and it takes some time to get there. Okay, it takes about 3-ish giga years, according to this simulation, to achieve equilibrium between magnetic and turbulence energies. Okay, but if you look at the right, if we don't use constraint transport, if we don't properly make sure divergence of B is 0, this is what we end up with. The magnetic energy absolutely explodes initially very, very quickly, and then takes over the thermal energy and also the turbulent energy. Basically, this is saying the magnetic field is the strongest contributor for all things in a galaxy, which is wrong. Okay. So I hope I have given you like a rough idea of how like people are using simulations to do any research related to astrophysics. I've probably introduced you to a little bit of why magnetic fields are important, and also importantly, how do you constrain a very difficult condition, which is divergence of B equals 0. At the crux of it, it is quite beautifully simple, which is you have a box and you solve at all surfaces. And instead of using the magnetic field itself, you use the magnetic flux and you use the Gauss law. These are basic principles that you already have, you had access to this information already, but it took people almost 30 years to figure out a nice way to implement it and to make it work. Okay, it's a long procedure. that has gone into it. The idea for a constrained transport scheme first came up in like 70s, but people were not very happy because you had to solve six phases algebraically simultaneously, which previously with very slow computers it was complicated to do, but now we can do it pretty quickly. And so in the 70s it was proposed. It took like 20 years for it to catch up. 90s people started writing codes like Flash, Athena++, and Enzo, where it was first implemented and used. And then obviously people saw drastic differences uh, when when they run their simulation with these two different methods. And then clearly one method took over the entire subject to become what is now the modern standard for evolving magnetic fields. Okay, I hope I've conveyed you that much, and also a little bit on the importance of resolution. How do you ensure resolution is concentrated in places where you need the resolution? Okay. um, yeah, I think that's the end of the talk. I had planned to also discuss how it is done in Aripo, where the grid is not fixed. Like I showed you, grid made of triangles, a grid that moves with the triangles. But yeah, there is no time for this. Okay. Any questions now? Yep. Mhm. Okay. So when it comes to optics, you're looking at quantum systems. You're looking at like very, very tiny things. And uh, in those scales, maybe there is something weird going on. But what we know from quantum mechanics is as you increase the scale, your quantum effects completely disappear. All your non-linearities completely disappear. They are so suppressed, you will never see them, right? And we are talking of scales that are galaxy sized, astronomical. So I think in this case, it makes no sense to think of a magnetic monopole, or, or at least something that is strong enough to be visible. Maybe at the quantum scale in the universe, there is some weird effect that is happening in the background. Maybe there is, but it must be happening at a very small scale that we will never resolve in this, right? So yeah, so I think it is like uh, pretty much well accepted that div b condition, div b equals zero condition is like mandatorily required in anything with like a large scale. Even in like solar physics related simulations, or people do simulations of small chunks of the solar surface. Even in such simulations, this must be satisfied. It is still a huge uh, system, a very classical system at that. Yeah. Mm. Yeah. Yeah. Unless like someone comes up and like throws everything off, and it must work with all other observations that we have, right? Yeah. So if people can come up with ways to do that, then I don't know.
Can
Then we
I
might be
can
looking
I
at something else 10, 20 years from now. But yeah, possibility is like
no?
zero, near zero. Yeah. Rishikesh, you had a
The
question.
thing is, no question, yes, but also just like a small